12th Science, Chapter Number 1, Solid State, Part 8, Imperfections in Solids.
Hello students, I am Madhusina, your chemistry teacher. Do like and subscribe my YouTube channel for further notifications. In this video, we will be discussing about different types of imperfections in solids.
The three-dimensional arrangement of constituent particles in a perfect order is known as crystals. Crystals are supposed to have an orderly arrangement of constituent particles, but in reality they do not possess the orderly arrangement. They may have imperfection due to presence of impurities or due to dislocation. Any deviation from the perfectly ordered arrangement of atoms, molecules or ions in the crystal is called imperfection or defect. The defects are classified into two categories: point defect and line defect. Point defects are the irregularities or deviations from the ideal arrangement around a point or an atom in an crystal, whereas line defects are the irregularities or deviation from the ideal arrangement in the entire row of lattice points. Point defects can be classified into three types: stoichiometric defects, non-stoichiometric defects, and impurity defects. Let us discuss each one in detail. Stoichiometric defects. If the imperfection in the crystal are such that the ratio between the cations and anions remains the same as represented by the molecular formula, the defect is called stoichiometric defect. These defects are also called thermodynamic defect or intrinsic defect. Further, stoichiometric defects are of two types: vacancy defect and interstitial defect. Vacancy defect. When some of the lattice sites are vacant, the crystal is said to have vacancy defect. This results in decrease in density of the substance. This defect develops when a substance is heated. Interstitial defect. When some constituent particles like atoms or molecules occupy the interstitial site, the crystal is said to have interstitial defect. This defect increases the density of the substance. The vacancy and interstitial defects can be shown by non-ionic solids. However, ionic solids must always maintain electrical neutrality. Hence, simple vacancy or interstitial defects are not shown by ionic solids. However, they show Schottky defect and interstitial defect. Let us understand this in detail. Schottky defect. It is basically a vacancy defect in ionic solids. In order to maintain electrical neutrality, the number of missing cation and anions are equal. Schottky defect is shown by those solids in which cations and anions are of almost similar sizes. Presence of large number of Schottky defect decreases the density of the solid. The number of such defects in ionic solid is quite significant. For example, NaCl, KCl, AgBr, CSCl, etc. shows Schottky defect. For example, in NaCl there are approximately 10 raised to power 6 Schottky pairs per centimeter cube at room temperature. In 1 centimeter cube there are about 10 to the power 22 ions. Thus, there is one Schottky defect per 10 raised to power 16 ions. Frankel defect. This defect is shown by the ionic solids. The smaller ion, usually cation, is dislocated from its normal site to an interstitial site. It creates a vacancy defect at its original site and an interstitial defect at its new location. Frankel defect is also known as dislocation defect. It does not change the density of the solid. Frankel defect is shown by ionic solids in which there is large difference in the size of the ions. For example, ZnS, AgCl, AgBr, AgI, etc. shows this defect. Silver bromide shows both Frankel defect and Schottky defect. Impurity defects. Introduction of defect in a crystal by adding an impurity is called impurity defect. This phenomenon is known as doping and the crystal is known as doped crystal. The defect in ionic solid may be introduced by adding impurity ions having different valence state as compared to the host one. As a result, a vacancy is introduced in the solid crystal. For example, if molten NaCl is crystallized with a little amount of strontium chloride, some of the sites of sodium ions are occupied by strontium ions. Each strontium ion replaces two sodium ions in order to maintain electrical neutrality. It occupies one of the site of sodium ion and the other site remains vacant. Other example of impurity defect is the solid solution of cadmium chloride and silver chloride. Non-stoichiometric defects. Some non-stoichiometric solids are known to contain the constituent elements in non-stoichiometric ratio due to the defects present in their crystal structure. These defects are either due to presence of excess of metal ions or deficiency of metal ions. These defects are of two types: metal excess defect and metal deficiency defect. Metal excess defect is due to presence of excess of metal ions. Such a defect is caused due to anionic vacancies or due to presence of extra cations at the interstitial sites. Metal excess defect due to anionic vacancies. Sometimes due to anionic vacancies, a local excess of positive charge is created at that lattice site. An electron can migrate to that site and get trapped in that anionic vacancy. Such a defect is called F-center. The letter F comes from a German word Farbenzenter, which means color. If the concentration of F-center in any crystal is high, then the colorless crystal develops color. This kind of defect is shown by alkali halides such as sodium chloride, potassium chloride, etc. Metal excess defect due to presence of extra cations at interstitial site. Zinc oxide is white in color at room temperature. On heating, it loses oxygen and turns yellow. This happens because excess of Zn+2 ion moves to interstitial site and electrons to the neighboring site. As a result, on heating, colorless zinc oxide turns yellow in color. The color is reflected due to excitation of electrons present in the interstitial sites. Crystals with either of these metal excess defect contain some of the free electrons, and such materials are semiconductors. Metal deficiency defect. There are many solids which are difficult to prepare in stoichiometric composition and contains less amount of metal as compared to stoichiometric proportion. Here, some of the metal ions are missing, and to maintain electrical neutrality of the crystal, its loss is made up by another cation of higher valence. For example, in FeO crystal, the amount of Fe ranges from 0.93 to 0.96%. In the crystal of FeO, some ferrous cations are missing, and the loss of positive charge is made up by the presence of required number of ferric ions.